Three-dimensional coordinate systems. Let's review the two-dimensional coordinate system. This coordinate system is formed when two lines meet at a right angle. One line we call the x-axis or the horizontal axis. The other line is the y-axis or the vertical axis. And we know that these two lines divide up the plane into four regions called quadrants. This is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. Furthermore, we also know that to locate a point in this system, we are simply lining up with the value on the x-axis and lining up with the value on the y-axis, and we call this point xy. And this system is sometimes called the rectangular coordinate system because a rectangle is formed. This system is useful when describing relationships between two variables. Often these variables are called x and y. But what if we have more variables? Particularly, what if we have three variables that have a relationship to each other? To discuss these kinds of relationships, we need a new system. We need the three-dimensional coordinate system. This system is comprised of three real number lines. We have a number line here, which I'm going to call the x-axis, a number line here, which is the y-axis, and these two lines are perpendicular to each other, even though it kind of doesn't look like it. There is a right angle here. And then we have a z-axis, a third axis, which is perpendicular to the other two axes. Now this x-axis here has a positive side and a negative side. The y-axis also has a positive side and a negative side. And the z-axis has a positive side and a negative side. To help us keep it straight in terms of how we draw this, well, let's talk about the right-hand rule. So if you put out your right hand and you curl in your three fingers here and point your index finger off to the side, your index finger would be the x-axis, the fingers pointing back at you would be the y-axis, and your thumb pointing straight up would be the z-axis. And this is helpful for keeping it straight in terms of which of these axes is x, y, and z. Now, how do we graph points in this system? To graph points, we simply need to line up the coordinates of that point on each of the three axes. So, for example, if I was going to graph the point 2, 3, 4, this would represent the point x equals 2, y equals 3, and z equals 4. And to do this, I would simply go to the number that is 2 units on the x-axis, 3 units on the y-axis, and 4 units on the z-axis. Now to graph this accurately, that can be a little bit challenging. But if I first graph the point 2, 3 in the xy plane down here, that would give us this point here. And now I need to go up 4 units from there and find out where z equals 4, and that would occur right here. So we have x equals 2, y equals 3, and z equals 4. And as you can see, this is often very challenging for students to graph in 3 dimensions. And some people are better at this than others. So to help us get a slightly better picture here, let's consider the point A, B, C, and we will assume that A, B, and C are all positive numbers. So the point A, B, C corresponds to A on the x-axis, B on the y-axis, and C on the z-axis. Another thing to consider is that the three-dimensional coordinate system has 3 different planes built into it. So the plane that contains the x and the y-axis, this is called the xy plane. The plane that contains the x and the z-axis is called the xz plane. And the plane containing the y-axis and the z-axis is called the yz plane. And this is helpful when we're having discussions about graphing in 3-dimensional coordinate systems. A lot of times we will refer to each of these 3 planes. Here is another picture of the point ABC graphed in the 3-dimensional coordinate system. This is a much better picture than the one that I attempted to draw just a couple of minutes ago. But you can see, once again, the point ABC corresponds to A on the x-axis, B on the y-axis, and C on the z-axis. And if you connect all these points here, you will see that you get a box or a prism. And you can compute the points at each of the corners of this box. So for example, down here we have the point 0, 0, 0. Right here, this is where x is equal to a, but y and z are both 0. That's because it is on the x-axis there. As I move out here, we have x equals a and y equals b, but z is still 0 because we have not gone up yet. And finally, up here we have the point a, b, and c. But again, there are other points that we could talk about. For example, the point at the corner of the box on the y-axis would be the point x equals 0 and z equals 0, but y is equal to b, etc. So you need to spend some time familiarizing yourself with this new system. Now let's talk about graphing equations in this coordinate system. So what would the set of points look like if the equation was z equals 3? Z equals 3 corresponds to all the points where z equals 3, and x and y can be any values whatsoever. So to graph this, what I would do is I would search for 3 on the z-axis, and so I'm just going to come in here and scale this out. Let's say that z equals 3 is right here. So this point would certainly be on that graph. But you have to imagine that x and y can be any values as well. So from this point, I can move out in the x direction or in the y direction as long as I don't move up or down, because z always has to be 3. So if you imagine doing this, what you would actually get is a plane, like so, where this point is on that plane. Okay, now again, this can be very tricky to draw, and I am certainly not an expert at drawing these graphs. But there are pictures in textbooks and online that can give you a much better idea of what this looks like. And I will actually import a picture in now. So this is a little better picture of what z equals 3 would look like. Now in the textbook, you will see them refer to R3. It almost looks like R cubed. That is the symbol that we use for 3-dimensional space. Okay, so we call this R3, and it simply represents 3-dimensional space. Now let's talk about y equals 5, the next one. How would we graph y equals 5? Well, y equals 5 would be all the points where y is equal to 5. So we have to find out where is 5 on the y-axis, and we're going to graph all points that line up with y equals 5. X and z can be whatever they want to be. So this is going to be another plane. It's a vertical plane this time. So the plane is going up and down. In fact, this plane is parallel to the xz plane. And that plane contains all the points where the y coordinate is 5 and the x and the z coordinate can be whatever they want to be. And I'll go ahead and import a picture of this as well. And this is a little better picture of what y equals 5 would be in three-dimensional space. As a note, the context matters when you start talking about 2 and 3 dimensions. So for example, if we are in 2 dimensions, which we call R2, x equals 2 is simply a line that lines up with x equals 2 on the x-axis, right? And so we know that this is a vertical line at x equals 2. But x equals 2 in three-dimensional space, in R3, is a plane, right? So if it's basically this line here is contained in this plane right here. Okay, so that line right there would be x equals 2 and z equals 0. So in other words, if we were to draw the graph of x equals 2, but only in the xy plane, it would look like this. Okay? But now this coordinate system here is simply laying down flat, and we have a z coordinate system perpendicular to it. And so when we talk about x equals 2 in three-dimensional space, we get a plane instead of a line. Let's take a look at another example. Which points x, y, z satisfy the equations x squared plus y squared equals 1 and z equals 3? So let's remind ourselves that if we have x squared plus y squared equals 1, in two-dimensional space, this is simply the unit circle. So in three-dimensional space, it's going to be that unit circle on the x and y axis here, but then also z has to be equal to 3. So x squared plus y squared equals 1 and z equals 3 is going to be the unit circle, but corresponding to 3 units on the z-axis. So if I come up 1, 2, 3 here, the circle x squared plus y squared equals 1 is going to be a circle with radius equal to 1. So the distance from here to here is 1 unit, from here to here is 1 unit. But it is lifted up 3 units because it has to correspond with z equals 3. Next, what does the equation x squared plus y squared equal 1 represent as a surface in R3? See, now z equals 3 is missing. And since it's missing, what that means is that z can be equal to anything. So we know that x squared plus y squared equals 1 is a unit circle, right? So if I go to x equals 1 on the x-axis, y equals 1 on the y-axis, and if I create a circle there, we know that this would be the unit circle in the xy plane. But since z can equal anything, we got to choose all the points that are above and below that circle as well. And so what we end up getting here is an infinite cylinder, right? So any point on this cylinder satisfies x squared plus y squared equals 1. And since z can be anything, it doesn't matter if z equals 1, if z equals 2, 3, 4, etc. Or in fact, if z is negative values as well. And finally, what solid region in R3 is represented by the inequalities x squared plus y squared is less than or equal to 1, and z is in between 2 and 4. So x squared plus y squared less than or equal to 1 would be all the points, once again, on the unit circle in the xy plane, but now we're going to shade it in. Because if it's less than or equal to 1, it's all the points on that circle and also inside of that circle. But z has to be a number between 2 and 4. So imagine that circle now. But if I go on the z-axis and I go up to x equals 2 and x equals 4, it's going to be all the points on the unit circle and inside of that unit circle, but at a height of 2 to 4 units. And so what that is going to look like is a cylinder here. And we're looking at all the points on the boundary of that cylinder and also inside of that cylinder. Now what I'm going to do next is bring in better pictures of all three of these examples. So here are better pictures of all three of these examples. So here is part A. We have the unit circle but lifted up 3 units. And again, the reason there are no other points here is because Z must be 3. So all the points have to be at a height of 3 units. And the next one, Z can be anything. So it's the same set of points on the outside here, but now Z can be at any level. So we take all the points on this infinite cylinder. And finally, for the last one, we have all the points on the edge of that circle and inside of that circle, and Z has to be at a height of 2 to 4. Okay, and so that's what we have here. So I hope these pictures help. Next, let's describe and sketch the surface in R3 represented by the equation y equals x. So again, in 2-dimensional space, if I have x and y equals x is simply a line. So the line y equals x in 3-dimensional space, so here is your x-axis, here is your y-axis. We're simply going to pick all the points where x and y are equal to each other. So the point x equals 1, y equals 1, x equals 2, y equals 2, etc. would be this line here. And it would also extend in the negative direction. But again, z is not mentioned in this equation. And that means that z can be anything. So not only do we take all the points on this line, but we take any point above the line or below the line. And so this is yet another plane. And I will bring in a better picture of this now. Now in this case here, you can see our x-axis is drawn a little bit differently, and our y-axis is here. And here is the line y equals x. And we're just showing the part of this plane that is in the first octant here. So we're showing it where x, y, and z are all positive, but this plane would continue on in this direction, and it would also continue on forever downward as well. The distance formula in 3 dimensions is very similar to the distance formula in 2 dimensions. In 2 dimensions, if I have a point P, which has coordinates x1, y1, and a point Q, which has coordinates x2, y2, we know the distance is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So in 3 dimensions, we just basically add another term to this and subtract the z coordinates of the points. So if I have 2 points P1 and P2, x1, y1, z1, and x2, y2, z2, the distance between these 2 points is given by a very similar formula. And this formula is just pretty much the Pythagorean theorem, but used in 3 dimensions. As an example, the distance between the point P, which has coordinates 2, -1, and 7, to the point Q, which has coordinates 1, -3, and 5, is distance between P and Q equals, and then what they're doing here is they're subtracting the x values, so 1 take away 2, squaring it, subtracting the y values, -3 take away -1, which becomes -3 plus 1, squaring it, and then 5 take away 7 and squaring it. And when you do the math on this, you end up with 3. So this is a very simple formula to use. Next, let's talk about the equation of a sphere. So in 3 dimensions, if you know the center of a sphere occurs at the point HKL, and if the radius of the sphere is equal to r, the equation of the sphere is x minus h quantity squared plus y minus k quantity squared plus z minus L quantity squared is equal to r squared. And if the center is at the origin, the equation simplifies to x squared plus y squared plus z squared is equal to r squared. And let's keep in mind that in 2 dimensions, we know the unit circle is x squared plus y squared is equal to r squared. Actually, that's not the unit circle, that's the circle. Radius equal to r and the center at the origin. So if you just take away the z out of this equation, you pretty much have the equation of a circle. So the equation of a sphere is very similar, and that's because a sphere is just a 3-dimensional circle. As an example, let's find the equation of the sphere with the center at the point 3, -1, and 6 that passes through the point 5, 2, and 3. So we know that the equation of a sphere is x minus h squared plus y minus k squared plus z minus L squared is equal to r squared. And these are the values of h, k, and L, because that corresponds to the center. And so this becomes x minus 3 squared plus y minus -1 squared plus z minus 6 squared is equal to r squared. And then we can simplify this just a little bit by changing this middle term here to be y plus 1 squared. But we don't know the value of the radius. However, since it must pass through the point 5, 2, 3, that means when x equals 5, y equals 2, and z equals 3, it must satisfy the equation. So if I plug that in, I'm going to get 5 take away 3 squared plus 2 plus 1 squared plus 3 take away 6 squared is equal to r squared. If I do the math here, this becomes 4 plus 9 plus 9 is equal to r squared. And this is 22 equals r squared. And now I'm just going to take the value for r squared and plug it back into the equation. So the equation of the sphere here should be x minus 3 squared plus y plus 1 squared plus z minus 6 squared is equal to 22. Next, we want to show that the following equation is the equation of a sphere, and then also find its center and its radius. So as I write down this equation, I'm going to reorder the terms a little bit. I'm going to put x squared plus 4x next to each other. Then I'll put positive y squared and negative 6y next to each other. And finally, positive z squared and positive 2z next to each other. And then the plus 6 here, I'm going to move that over to the other side. Now the reason I'm doing this is because next step here is going to be completing the square. So to complete the square here, I need to add 4. And if I do that there, I need to add 4 to the other side as well. Next, to complete the square here, I need to add 9. And we'll add 9 to the other side as well. And finally, to complete the square here, I need to add 1. And that means I need to add 1 to the other side. And the reason we do this now is because each one of these can be factored. This can be factored into x plus 2 quantity squared. This one becomes y minus 3 quantity squared. And this one becomes z plus 1 quantity squared. And on the other side, we're just going to add all these up. And when you do that, you should get 8. And so the center of this sphere occurs at x equals -2, y equals 3, z equals -1. And the radius, remember now, this number is the radius squared. So the radius is the square root of 8, which can be simplified to 2 radical 2. And finally, what region in R3 is represented by the following inequalities? We have x squared plus y squared plus z squared is in between positive 4 and positive 1. And we have z must be less than or equal to 0. Well, let's think about the first part. We know that x squared plus y squared plus z squared equals 4 would be a sphere of radius 2. So if I go out 2 units in all directions, we would simply draw a sphere, a ball, that goes through all of these points. Okay, but we also know that it needs to be equal to 1. So that would be a sphere that goes through these points, right? Because that would be a radius of 1. And we want all the points that are in between these two spheres. So first I'll just start by drawing a circle here and a circle here. We want all the numbers inside of the larger circle, but outside of the smaller circle. Now, that's the two-dimensional version, but this is a three-dimensional sphere, so we need to go to z equals 2, which would be down below here. And we are looking at that bottom half of that sphere within a sphere. So what we're looking at there is just the points that are in between these. So if you kind of imagine having a peanut M&M, and if you imagine that peanut M&M being a perfect ball, a perfect circle like this, and it's got a peanut on the inside, which is another perfect ball, what we're basically doing is cutting that M&M in half, taking out the peanut, and all we have left is that bottom half of the sphere with the inside cut out. Now I'll go ahead and bring in a better picture, and hopefully that will help you understand it. All right, so hopefully this gives you a little better picture of what's happening. And that concludes this video lesson.